Hi, welcome to PI Tech Talk. Analog to digital converter, or ADC for shorts, are really useful peripherals and that have many uses. And the versatility also driving the various features and demands we put on it. In this video I will start scraping on the fundamentals regarding the ADC. Here is a block diagram of a typical A to D converter. In the left you have a lot of sensors, and they are then fed to the multiplexer, which select one input at a time, feed that analog voltage to the programmable amplifier, and then feed that signal in his turn to the ADC to be converted. There are many types of ADC. In this slide I have taken up three of the most common ones. And SAR is the one that we are going to take a look on in this episode. And it says a successive approximation, and it have a resolution normally from 8 to 18 bit. And in this STM32 we have a SAR for 12 bit. And the speed is normally up to 10 megasamples per second, and the G71 is maxed out at 2.5 megasamples. There is also one more common type, this is called delta sigma, that actually can generate very high resolution but to a very low speed. So I think that the SAR is a good common ground. Here we have a representation of a 4-bit SAR. So up in the left corner we have the voltage in, and that comes from the multiplexer, and then it's fed into the sample and hold register. That holds the value constant during the conversion phase. Then it feeds that information to the non-inverting input to the comparator. To try to explain how the SAR works, I will work with the voltage reference on 16 volts, and that is an unrealistic voltage, it's much less. And I also work with the hypothesis that the input voltage is 10.4 volts. And this is what we are using for it. When you reset or start the conversion, the SAR put his MSB, the most significant bit, high and the rest low, driving the DAC to output half of its voltage reference, and that means that it outputs 8 volt, and that put that into the non-inverting comparator. In this table we have the lower x-axis is the number of clock cycles, the reset cycle, the first, the second, the third and the fourth. We only have a 4-bit ADC, so we only have 4 cycles. And on the Y cycle you have the voltage rails from 0 to 16 volts. And that small yellow line is indicating the input voltage on 10.4 volt. When we start the ADC conversion, the SAR put its MSB high, driving the voltage out from the DAC to half of its voltage reference, indicating that you get 8 volt out. So that is what you see in the first blue box there. And then you have the digits 1004. And that is then compared by the comparator, and it's in the control circuit says that it's lower than the input voltage. So then you instruct the SAR to, in the next clock cycle, to increase the voltage. So it puts its second most significant bit also high. That drives the DAC then to output 12 volt. However, the 12 volt is higher than the input voltage on 10.4 volts. So the control circuit says, okay, you overshoot, it was too much. So you can't take that next most significant bit. So you need to take that as a 0. So in the third step you see there it's 1 0. And it puts then a 1 again, and then you drive the output voltage a bit closer, then still at 10 volt, but still you still undershoot, and the control circuit says, okay, you are closer but you need to get even higher. So then you remain that digit and you drive a next cycle, you add a bit more voltage, and that way you shoot over and under until you find the right value, or you run out of a number of bits. So this is how the SAR works, and you can count on the number of cycles because you know that if you have 4 bits, you have 4 cycles to count. So if you have a 12-bit ADC, you have 12 clock cycles to run the full conversion. The voltage reference is extremely important. If you have a bad voltage reference, you have a bad A to D converter. So that is really important and need to be taken into consideration. In this overview of the power domain, you can see that there is a separate VREF pin. And in application where resolution is not a major demand, you can use the VDD to power the VREF pin. Or if you have higher demand, you can also put an external voltage reference to source this pin. Or you can also use the internal voltage reference buffer that is available on this device. This device has the internal voltage ref buffer, and it's configurable to either 2.5 or 2.048 volt. But why are there 2 different voltage rails available, and why such an odd voltage as 2.048 volt? If we take a look in this table, we can see that the resolution we ideally can get is depending on the different VREF. Here we can see the benefit of having a 2.048 volt. That is because the resolution is 0.5 millivolt instead of getting many decimal points. Please make sure that the sample voltage you are feeding to the sample and hold don't exceed the VREF. We have been discussing the ADC as an ideal component, but you need to think about the ENOB, and that stands for efficient number of bits. And in an ADC in a built-in microcontroller, you normally get 1 to 2 bit that is lost in the end on the LSBs due to noise. You also need to think about temperature drift, linearity, and also please consider the VREF. It's crucial that you have a good voltage reference and you don't have 2 noisy pins on the VREF. Now I hope you got a bit more basic understanding in the topics of SAR ADCs. This topic can be really easy and also be very complicated, depending on your requirements. As always, if you learned something and you liked the video, hit the like button. And if you're not yet a subscriber, then you are a part of the 83% portion of my viewers. See if we can improve on this. It's free and you can just hit the round icon in the left. Until I see you next time, stay safe.